Hello, class. I have a great lecture ready for you on ideal op-amps and the inverting amplifier and the non-inverting amplifier. And you'll find this in chapter 5 of your textbook. But I want to point out that I am the only professor that's teaching Network Theory 1 that actually is going to go through and agrees with Alexander and Sadiku, the authors of your textbook, that it's a good topic to cover, even though you're not really going to get into analog amplifiers until you get into analog circuits, which comes after Network Theory 2, right? So, but what I have found in teaching Network Theory 1 for a couple years now is that if I introduce this package, and I'm going to give you a couple things that you can look into on your own. The 741 OpAmp is the main OpAmp that we use at Wentworth for. It's a very robust and rugged OpAmp that can use a whole variety of different things. And when we look at an OpAmp, an operational amplifier, I'm just going to draw the symbol for it here. It looks like a triangle, an isosceles triangle or an equilateral triangle that's pointed in this direction. And it's got two inputs, but then it also has two voltage supplies. So this would be the positive voltage supply. This would be the negative voltage supply. And when we look at op-amps and we look at the positive and negative supply voltages, what we see is that those can go from 0 all the way up until about plus and minus 18 volts, right? So if you were setting something up here, and it depends on how the operational amplifier works if you have the correct thing. So the maximum supply that you can put in there is 18 volts. And in fact, the thing will work probably from 18 volts down to about 3 volts, although you won't be able to do as much with it. You'll only be able to do some very, very low frequency or low power things if you're just powering it with 3 volts, but you'll be able to actually get something that'll come out of there and work. If it's below that, I don't even think the op-amp would work, and I've certainly never run an op-amp at 3 volts, but I believe it's possible. Usually you run the op-amp around 15 to 18 volts, or if you're working with a battery supply for a printed circuit board that uses an op-amp, you could always use plus and minus 9 volts using a 9-volt battery, 2 9-volt batteries, and then hitching them up so that they would give you a positive and a negative 9 volts. All right, so those are going to be the supply voltages, but here are the two input voltages. One is called the inverted voltage, and let's say that that's the negative input or the inverting input. Now put the non-inverting input. So this is called the inverting input, and this is the non-inverting input, right? One's a negative, one's a positive, but that's not how the operational amplifier really works. And as you start to read through chapter 5, what you see is that there's various characteristics with an operational amplifier, and the things that we use when we're doing analysis using KVL and KCL analysis, Kirchhoff's voltage law, Kirchhoff's current law analysis on an operational amplifier, what we have to take into account is that the impedance at the input, so input impedance, think of it as resistance at your level, is infinite, right? So no current can flow into an operational amplifier's inputs. No current flows, that's right, it's important enough for me to write it, into the input of an OpAmp. Now that's not entirely true, but usually the front end, we call this the front end of the OpAmp, and we call this the output of the OpAmp. Right? So the front end of the OpAmp has an infinite. In fact, it's not really infinite. It's more like 2 mega ohms, but really that's pretty infinite compared to everything else you've gotten. And the output of so you've got infinite input impedance, right? No current flows in there, but you only have you have 0. Theoretically, it would be 0 impedance at the output. So 0 impedance at the output, infinite impedance at the input. And you've got another thing, because we've got infinite input impedance at the input. V minus always wants to equal V plus. So whatever voltage is on one of these, if I ground one of these, the other one wants to get to 0. If I were to set one of these up at 5 volts, the other one wants to get to 5 volts. That's what it wants to do. So I'm just going to do some analysis of that right now. But I want to point out to you that I'm not going to go into the internal workings and how an op-amp is fabricated, and you know how what the basic formula, I should say circuit of an op-amp is. It's very complicated, and it's really a differential amplifier, not a difference amplifier, which I may show you in the next lecture, but a differential amplifier that is the basis of the op-amp. And the op-amp, by the way, is very old. This really goes back to the late 40s, early 50s, when we used operational amplifiers in the first computer. That's what they were used for. They were used as analog computers originally. All right, I've realized now that I have absolutely nothing to drink, nor have I had anything to drink since the first lecture I did a little earlier this morning, but we'll see how far. I might have to make a little pause just to go grab a glass of water, but we'll see how far I can go in this lecture. Again, I don't want this lecture, I don't want you to think that I'm teaching you everything that you're ever going to learn about an op-amp. You've got about 3 or 4 lectures in both network theory 2, touch on op-amps maybe in network theory 2, but also in your analog circuits class. The whole first part of that is going to be discussing operational amplifiers and all of what is going on inside an operational amplifier. So I'm not going to do that, but what I'm going to do is these are called active, right, circuits. Why do we call them active circuits? Because they are using the op-amp rather than just passive components. So this would be an active circuit amplifier that we're using. Now, I want to draw the inverting amplifier. I'm going to derive 2 amplifiers and talk about why these things are amplifiers, right? There's 2 things that we have to remember, though, is this is one of them. I should circle that in red, but I'm going to circle it in black, and I'm going to put a couple stars next to it, right? Those always want to be the same. Another thing that I want to write down in here is I plus equals I minus equals 0 amps. There's no current flowing into any of those 2. And of course, I can only write it here as many times. We're going to use that. We're going to use that to do a Kirchhoff's current analysis on a node inside the circuit that I'm going to draw right now. And this is a circuit that you're going to see a lot of times throughout your life. You're going to make this circuit so many times and so many different circuits that you're going to design. So anyway, I'm going to draw the whole circuit. This is my output, right? And my input then is going to have a resistor in it. I'll call that Rn. I'm going to call it Rn. I know that you're saying, well, maybe we should call it R1 or whatever. No, the book might call it R1. I want to go with what you're going to be seeing these things as for the rest of your lives, right? This is going to be R sub F. So I'm going to call my feedback resistor R sub F, and I'm going to call my input resistor Rn. Now, I'm also going to tie that into ground, right? Then I'm going to say that I have a voltage V1 coming in here. Actually, why don't I call it V in? So I've got my voltage V in coming in here. And if you wanted to think of that as some type of positive DC voltage, right? And then I could connect that up to my ground so that I have the full circuit as it looks here. This is connected to ground though. So let's not forget that I've got my inverting here and my non-inverting here, right? Just like I've drawn it over here. Now, what do we know? We know that V minus wants to equal V plus, doesn't it? And we know V plus is tied right into ground. So we know V plus equals 0 volts and V minus equals 0 volts because they're internally connected and they're trying to get to exactly the same voltage. V in, right, to DC voltage. I'll do an example after this, but I'm trying to do this symbolically right now. So let's look at, since we know there's no current, right? We've got current that's flowing around here. So let's get some current. So I've got current that flows out of here and it flows through that resistor. It comes to this node. There's no current that flows into an OpAmp, right? So the current now is going to go this way. Does everyone see that? Does everyone see the current direction that we've got here? Excuse me. Yeah, I've been doing some lectures lately. So let's look at the voltage drop, right? So if that's true, if the current that's going through there is, you know, the same, we know that the current, isn't this all one current? Let me get another color here, right? If this is all the same current, then we know the current, I'll call this I1, and I'll call the current through here I2. But I think everybody can see that I1 must equal I2, right? Because they're all the same current. And there's only one current path here, so I1 has to equal I2, has to equal I. I'm just going to call it I rather than I1 and I2 because we know that the current that is I1 is the current that is I2, so we don't really have to worry about that. But let's just write these because we know that V equals IR, don't we? V equals IR. Or I equals V over R, doesn't it? And we know I1 equals I2. So let's do that. So I1, what is I1? I1 would be V in minus V negative, V inverting, divided by R in, right? So this is I1. Now, what's I2? Well, I2 would be V minus, or V inverting, minus V output, right? Because that's V output. V minus right here, V output, divided by R sub F. So we know that has to be true because we're just using Ohm's law, and we figured out what that is. Now, we do know some things about V minus and V plus. We know that V minus and V plus, because V plus is, tied into ground, is got to be 0 volts. So let's extend this over. So that would mean that I would have V in minus 0. So I have V in divided by R in, right? Because that's 0. So V in minus 0 gives me V in over R in. What does that equal? Well, we know this is 0 minus V out. So I've got minus V out over R sub F. Well, let's solve for V out. Right, so if I get V out, in fact, I should probably put it up there. When we get V out, I'm going to have to bring the R sub F out of the denominator on the right-hand side into the numerator on the left-hand side, and I'm going to have to take that minus and throw it out there too, won't I? Right, so that equals minus R sub F divided by R in, right, times V in. Now that is a relationship and the inverting amplifier, right? This is the inverting amplifier. Let me use my super giant pen here. The inverting amplifier, right, is right down here. Right? And here is our relationship for the inverting amplifier. So anytime that you want to hitch up an op-amp like this, and I do want to point out that when you're talking about, hitching up an op-amp, like I say, it is a IC chip. And so the IC chip is going to look like this. Pay close attention to what I'm telling you right now, because this is, a very salient point, and you're going to, as electrical engineers, need to know this for the rest of your life. So when you look at a chip, and the 741 OpAmp has 4 legs on both sides, right? A lot of them also have what's called a slot here. And you'll see it's just a little indentation. And when you see the slot like that, you'll always know that pin 1 is over here. 1, 2, 3, 4, 5, 6, 7, 8. That's how it goes, right? Sometimes you'll also see a little indentation where pin 1 is. 1, 2, 3, 4, 5, 6, 7, 8. Now, when you want to use this chip and you want to put that chip inside your breadboard and use it and everything else, you would ground these and you'd have to get a schematic of what the individual pins go to and everything else. We will probably do, I might give you an extra lab on this that you can do at home. And I would say also practice, with my thing and everything else, practice putting one of those together. Now, I can't give you the pinout. I don't have the pinout right off the top of my head. I probably should have printed one of those out, and I might, I'll do that for the next lecture, because the next lecture is going to be on summing amplifiers and difference amplifiers with OpAmps. And so I'll try to give you a pinout. You could actually do this. Just look up the pinout. This would be the pinout for that IC chip, the 741 OpAmp that I'm talking about. There are other OpAmps too. There's a whole variety of different manufacturers and different flavors of OpAmp. There are audio OpAmps for higher power. There are signal OpAmps. There are very robust OpAmps like this. There are very vulnerable OpAmps too, right? So there's a lot of things to do with IC chips, and you're learning about them right now in what I'm teaching you here about the 741. But you'll also have something that will give you the pinouts on the operational amplifier itself, so that it would have, I think the output is 6, the inverting is 2, the non-inverting, off the top of my head, I can't remember what that is. I think this was 7 and 4 as far as my supply voltages go. That's the negative supply, so that'd be your minus 18, and this would be the positive supply voltage. That would be your positive 18 volts or positive 15 volts, something like that, whatever your regime you're working on. You can't go higher than 18 though. And so you would use all of the pinouts that would be on there. And I say just Google pinouts for 741 OpAmp, and it will show you this. But in the next lecture, I'll show you. I'll actually draw one up and show you. I'll download one off the internet. I can't remember all the pinouts off the top of my head, but that's not that hard. All right, so we have done the derivation for the inverting OpAmp. Now what I want to do is I want to look at the non-inverting OpAmp, and and derive its relationship. So you can see here, if I was actually do that, what would happen if I put an OpAmp together that was like this? I'm just going to bring this down. Let's just do an example. Let's say that I had 1 volt that was going into, better put a resistor there, that was going in, and then I had a feedback resistor coming out just like that. This was grounded, just like you would see. That's going to be my non-inverting. That's my inverting input. I've got 1 going in. And let's say that my input resistor is, I don't know, 1,000 ohms. And my feedback resistor is 10,000 ohms. What's going to come out the other side? What is my output? I think everybody can see that my output, can you still see that? Yeah, my output is going to be 10 volts, isn't it? Because I put in 1 volt, and then it's just going to be, oh, did I say it should be minus 10 volts? Thank you, because it's a minus, isn't it? So I've got 1 volt going in, a 10 to 1, but don't forget the minus. So what I get my output is going to be minus 10 volts. I hope everyone sees how that's working, and I'm going to have a big drink of water, I think, when I get done with this lecture, but I don't know if I want to interrupt it right now because we're getting into the derivation of the non-inverting OpAmp, and it is going to be exactly similar as far as the derivation goes. It's going to be very similar, but it's a more complicated circuit. And I want to show that to everybody. Your book has drawn it very well. I don't really draw it all that well, like your book has done, but let's just see what we've got here. So this is going to be V out, right? And I'm drawing it much the same way that I drew this one. But instead, the non-inverting or the inverting input, instead of going back, it still has its resistor, and I'm still calling that resistor Rn, right? I'm still going to call that Rn. But now this is going to go to ground. So I'm going to ground this out. Am I still going to keep my feedback resistor on this part of the network? Yes. So my feedback resistor is here. My input resistor, in fact, all of this looks exactly the same, except instead of this going to V in, it's going to ground. And this other one, right? This other one is going to go to V in, right? And since I'm putting this to ground, and that could go up to ground too, doesn't really matter. They're all grounded, is what I'm saying. So this is V in DC, V in, right here. Just like VN was connected to the non-inverting in this for the inverting amplifier, VN is connected to the positive or non-inverting terminal in here. Now we want to do, they're all connected to ground is all I'm saying. Now let's look at the voltage of the minus and the plus. So we know the voltage of the non-inverting input is going to be VN, right? You know, if that is the voltage of the non-inverting input, isn't that what the inverting input wants to be too? Right? Because the inverting input and the non-inverting input always want to be the same. Just like when we saw up here that this was 0, so we knew that was 0. We knew this was a virtual ground. If this is 0, that's 0. So if this is VN, then that's VN too. So we also know that that is the inverting input's voltage too, isn't it? Now, let's look at this. So we know that V equals 0 here. I probably even shouldn't have tied those together, but you know, just put 2. Yeah, why don't I do that? Just so I don't want to confuse anybody. Just gonna, you know, that's grounded. Hey, this is grounded over here. Whatever. That's just saying that this voltage that's going in there is going to be a certain level of voltage off ground, right? So that's what we've got. Now, we also know there's no current that's flowing into either one of these two, right? We know they have to be the same voltage, and we know there's no current flowing into either one of those two. So just like before, I assume that the current, right, that's flowing, the direction that I'm going here is going to be from here to here, right? There's no current flowing in here. There's no current flowing in there. So that's not moving. That's just staying the same. It's just staying VN. And if that stays VN, then that means this has to be VN as well. So let's do our Kirchhoff's current analysis on that node. In fact, what I want to do is I'm just going to circle this node. This is a very important node, right? In the last example, that node was a virtual ground. Let's write that. That node was called a virtual ground. It's not a ground, it's not hitched up to ground, but because this is hitched up to ground, this becomes a virtual ground. Now this is hitched up to VN, so that becomes VN, doesn't it? So let's do our analysis again, just like we did the last time. So we know if I say that this, again, just like I did before, this is I1, and this is I2, we can see that I1 and I2 have to be exactly the same, right? So I1 must equal, because they're the same current, I2. So we can look at the current, I1 equals I2, and just write down what I1 is. So I1 is going to be 0 minus V inverted divided by Rn. Right? And we know that that's got to equal V inverting minus V out divided by R of the feedback loop, right? So we know that those two are going to be, in fact, what we could do is we can just solve this. 0 minus Vn is just going to give me minus V in divided by R in, right? So there's the, wait, what did I got there? 0 minus, oh, you know, I should have just left that at, I mean, I think everybody can see that it's going to be Vn, but I'm a little ahead of myself. So let's just put V inverted there. And then I can write the next one, minus V in, because we know V inverted is V in, right? V inverted is V in, so I can just write that minus V in over R in. All right. And I've got this here. Now I can also say that this is going to be V in, right? Because V inverted equals V in. Right? So let's do that. So V in minus V out over my feedback resistor has got to equal minus V in over R in. All right. Now, all I want to do is simplify that. So I can think everybody can see that this is V in over RF minus V out over RF. So the first thing I want to do is I want to try and get V out all by itself. So let's take the other side and multiply it by that. So I get, in fact, I probably, yeah, well, I could do that. That's fine. So I get V in, I'll do it in 2 steps. I don't want to lose anybody, equals minus V in times, I could put the minus there. I could put the minus R sub F over R in. It's not like this is the last time I'm going to write it anyway, so I can clean it up in just a second. So that's minus V in and, you know, everything. And I've got V in, but what I want really is I want V out by itself, right? So let's take V out, which is negative here, throw it on the other side of the equation and bring this over onto the right-hand side of the equation. So I get V out positive now because I brought it over to the other side of the equation. Then I'm going to bring this back into this side of the equation, which is V in plus V, V in times R sub F over R in. Almost done. So let's just look at this equation right here. We can simplify it a little bit. You can see that I've got V in both of those two different things. So what we end up getting is that V out, right, with the amplification of V out is going to be V in times 1 plus R sub F over R in. Right? And so that is your relationship when you construct the non-inverting OpAmp. This is your relationship between the output and the input. Okay, I'm going to use my super giant marker and just draw that over there. Okay, so V out is V in 1 plus R sub F over R in for the non-inverting amplifier. And for the inverting amplifier, V out is minus, so it's 180 degrees out of phase for AC, but minus R sub F over R in. What if I wanted to do the same thing? So now I have V in equals 1 volt. And I have R sub F equals 2200 ohms, and R in equals 330 ohms. What's my amplification going to be? What is my V out going to be? I think everybody can see that 2200 divided by 330, wait, don't tell me, 2200 divided by 330 is 6.67. So V out would be positive 6.667 volts. Does everyone see that? You know, we did a little example there, we did a little example there, but this is just an introduction to the inverting and non-inverting OpAmp. You're going to use that a bit and definitely see it again. And oh, there we go, time's up. So I'm gonna have to, that went on a little bit longer than I thought it was going to, but I wanna give you a good introduction. Start getting that in the lab or using it, lab at home or whatever. And, start building your operational amplifiers. We should give you guys all a cadet board. All right, on to the next lecture.